Okay, so after we take a look at all of these different definitions of acids and bases and conjugate acids and bases and buffer systems, there's one more thing that we want to take a look at, and that's basically applying stoichiometry to acid-base reactions. And honestly, you've done this several times throughout the semester, but there's a special type of stoichiometry calculation that we tend to introduce along with the acid-base chapter, and that's called titrations. So again, don't be afraid of the word titration. A lot of people kind of freeze up when they hear that because they think, oh, that must be really complicated. And really all it is the stoichiometry you already know how to do. So just another type of stoichiometry with solutions. So that just means we're going to be using concentrations like molarities and volumes to be able to keep track of moles of the acids and bases. So let's say that I have HCl, and I'm going to react that with calcium hydroxide. Now at this point, you should be able to tell me what those products are and write a balanced reaction for that. It would be a really good thing for you to pause now and make sure that you can still do that. But for now, we're just going to go ahead. And we've got calcium chloride. So here's our balanced reaction. Now, a titration is a very specific kind of experiment. So let's say that I have, and this is typically what you would do experimentally. I've mixed up a solution of hydrochloric acid that I think is pretty close to a certain concentration. But a lot of times we need to figure out, is it exactly that concentration? And the best way to do that is react it with something else and work backwards and figure out what that concentration truly is. So we do a lot of standardization. So figuring out exactly what is that concentration from an experimental set of data. So let's say that I gave you this reaction. I said I'm reacting some unknown concentration of HCl. I don't know the molarity, but let's say I told you I took 25 milliliters of that unknown solution, and I'm going to react it with calcium hydroxide. And I'm going to react it with calcium hydroxide, and let's say that that concentration is 0.0495 molar. I'm not going to tell you the volume yet because I want to show you how that's arrived at. So over here, let's picture this experiment. So I start out with a beaker with my 25 milliliters of unknown concentration HCl. That's the stuff in the beaker. So I don't know how many moles of HCl are there. I don't know what its concentration is. My goal is to figure that out. Now the way that I figure that out is I then load up a burette, something that will help me keep track of volumes, with the calcium hydroxide solution. I do know its concentration. I also know a starting point, so I fill it up, and I have these markings that keep track of volumes that I would actually dispense from it. And there's a little valve here, and we open that, and we just drip the calcium hydroxide into the HCl. And we know that those two things react with each other because we've got an acid and we've got a base reacting. Now, we use a special term to describe when they exactly react with one another. So when all of the moles of HCl in this solution are reacted with calcium hydroxide that get added. And that term is called the end point. So the end point is where all of the acid and base reactant are used up. Really what that's telling us is there's no limiting reactant to this particular reaction. All of the HCl is gone, and I've added just the right amount of calcium hydroxide to react. And I've got a balanced reaction that will help me relate those two things to one another. How do I know I've gotten to the end point when I'm doing this reaction? This is a clear colorless solution, and this is a clear colorless solution. There's a couple different ways to do it, but one of the traditional methods is to add something called an indicator. So we put a few drops of something called an indicator into this solution, and it changes color when the pH shows the end point. And knowing where that end point is at on the pH scale differs depending on if we're doing strong acid and strong base or weak acid and strong base, and that is beyond the scope of what we're doing this semester. But just understand that we pick an indicator, something that changes color when that stoichiometry is perfect between the acid and the base. The other thing I just want to throw in there as a comment is titrations don't just talk about acid-base reactions. We could talk about a precipitation titration, an oxidation and reduction titration. All it means is I'm looking at the relationship between the two reactants. And a lot of times it's in solution. That's the other thing that they have in common. But again, it's just typical that these kind of calculations show up in the acid-base chapter. So we find out what the end point is. This turns color after we've added a certain amount of the calcium hydroxide. And let's say we look on our burette and we measure the volume added to be 47.8 milliliters right at the end point. So I'm going to take this value, again it's experimentally determined, and I'm going to move that over here because I know I used 47.8 milliliters of this concentration calcium hydroxide solution to exactly react with 25 milliliters of this HCl solution. So now that you look at that, if I told you these two pieces of information about the calcium hydroxide volume here and asked you to find the molarity of HCl, without even talking about this being a titration or an acid-base reaction, you should be able to do that. We did this back in the solutions chapter, and we also looked at the relationships between reactants when we just did stoichiometry in chapter 8. Can I find the number of moles of calcium hydroxide that got reacted or used up? And I'm hoping you answer yes to that. If I know volume and molarity, I can find moles. So if I find moles of this, I can use this 1:2 ratio to find moles of HCl. If I know moles and volume, can I find molarity? And the answer is yes. That is my exact definition of molarity. I am looking for the moles of HCl that are contained in the 0.025 liters of that solution. So I'm trying to fill in this blank so I can calculate the molarity. And I can do that starting with these pieces of information here. So if I start with 0.0495 moles of calcium hydroxide per liter, and I'm using 0.0478 liters of that solution, if I multiply those two numbers, I know at that point the moles of calcium hydroxide that were reacted. If I know the moles of calcium hydroxide, I can use my mole ratio from the balanced reaction. I know every time I use 1 mole of calcium hydroxide, I also use up 2 moles of HCl. Now I know moles of HCl. This is the number I was looking for, so I could plug it into this equation to find the concentration. So let's just do that. And I get 4.732, and I'm keeping a few extra digits here because I don't want to round before I'm done with my calculations. So 4.732 times 10 to the minus third moles of HCl. I'm going to take that over here and plug it in. 4.732 times 10 to the minus third moles of HCl were contained in that 25 milliliters, or the 0.025 liters of that solution. if I solve for that molarity, I get 0.189 molar HCl. Had to be what I started with. Now, this is how those solution concentrations are determined. If you go to lab, the stockroom people mix up the solutions and approximately get them to 0.1, maybe they were aiming for 0.190. But there are complications with making a lot of these solutions. So they make it, get it in the right ballpark, and then they go through and do a titration several times to figure out what is the actual concentration there. So your lab manual might refer to, use the approximately 0.190 molar HCl, and you go over to the carboy and it says 0.189 on it. Well, that's because this is the actual concentration that solution ended up being after they checked it. So that's why these numbers aren't nice and pretty on a lot of the carboys, because experiments are messy and they don't always turn out perfectly. So that's where that comes from. So again, it's just stoichiometry using acids and bases. And using the terminology endpoint is really the critical piece here. The endpoint just means I have exactly the right number of moles of these two substances to react with each other, no more, no less, no limiting reactant. So try practicing some of those, applying what you know about stoichiometry and your volumes and molarities. The other thing that I will point out is some of you were probably tempted to use M1V1 equals M2V2 to do this problem. And I'll tell you, you got the wrong answer. And I want you to understand that M1V1 equals M2V2 is a dilution calculation. We are reacting things, not diluting them. Okay, so it's just not an appropriate place to use that formula, and just make sure that you understand you can't do that here, or you will end up with the incorrect value at the end. So practice some of those, and again, bring questions to office hours or to the tutor room, whatever you need to do. Make sure you understand how to do those problems.